Welcome everyone again, and in today's video we are going to talk about relative velocity. So when you're talking about relative velocity, this is just the velocity of an object as measured by an observer who may be also moving. So when you're talking about the relative velocity, here we are just trying to relate the velocities of two objects. But in relation with the mostly the observer, the one who is observing. So different observers can measure different velocities for the same for the same object. Now again, another thing that we have in relative velocity is what we have, which is reference frame. So what is this reference frame? So when we are talking about a reference frame, this is just a point where the observation are being made by the what? By the observer. So it's the coordinate system or point of view of the observer from which measurements are made. So examples of reference frames that can be there are, for example, earth or a car or bus moving with constant speed, a train, boat, or airplane. So those are just what reference frames. So away from that, let's look at an example. So an example that we have is two cars moving in the same direction. We have car A and car B, and car A moves at 60 km per hour and car B moves at 50 km per hour. So these are the cars that we have. Now the observed speeds that are there is VA, which is velocity of car A, is what is 60 km per hour. Velocity of car B is 50 kilometers per hour. Now, what's the relative velocity of A with respect to B? So the velocity of A with respect to B. So the way we write these relative velocities, we start with, for example, the relative velocity of A. We start VA with respect to B. That's where we put B. And again, we are going to get the formula for relative velocity. For example, for this one, it's VAB is equal to VA minus VB. We start with the one which is having the relative velocity of A with respect to what to B. At the end, the relative velocity is what? 60 minus 50, which is 10 km per hour. So the key takeaway there is the measured velocity of an object depends on the motion of the what? Of the observer. Now let's talk about the relative velocity equation. So we are trying to relate velocities between what? Between observers. So we are going to find that to connect the motion of one object as seen by another observer, we usually use the relative velocity equation, which is the general equation in one dimension. It's this one, which is VAB is equal to VAE minus BE. So where VAB is the velocity of A relative to what? To B. How A moves as seen by observer in what? In B. While VAE is velocity of A relative to S, or reference frame E. VBE is velocity of B relative to what? To F. Now, how do you find the answer for velocity of A relative to B? We say VAB minus is equal to VAE minus BE. So what's the meaning there is velocity of A relative to B equals velocity of A relative to F minus velocity of B relative to what? To F. So that's a general equation for what? For relative velocity. And what's there is, you have an example here, two cars moving in the same direction. We have car A travels east at 20 km per hour and car B travels east at 50 km per hour. What is the velocity of A relative to B? So it's going to be VAB is equal to, where the equation VAB is equal to VAE, which is 80 km per hour, minus VBE, which is 50 km per hour, getting 30 km per hour east. So that's the answer for VAB. So the interpretation that is there is to the driver of car B, car A appears to move at 30 km per hour east. So to the driver of car B, this driver here, since he is the one we are taking as an observer, this car, which is car A, is appearing to move at 30 km per hour. Another thing is important thing that's there, if the observer is moving in the same direction as A, subtract the speeds. If they are moving in opposite directions, subtracting automatically becomes what? Becomes addition. So let's look at another thing. So here we are just trying to look at applications in one dimension. or relative. So we have some relative velocity examples. So we can use the relative velocity equation to solve real-world problems involving objects moving in the same or opposite direction. So let's look at example 2 here. We see that car A, which is this car A, travels east at 60 km per hour. Then car B travels west at 40 km per hour. Now what's there is to find the VAB, A relative to B, what's there is VAE, it's positive. It's moving in the VAE is moving in the positive direction. What about VBE? It's moving in the negative direction. So when we are going to write the equation, it's going to be VAB is equal to VAE minus VE. And where there is VAE, we put 60 km per hour minus, since that one is negative, it's going to be 60 minus negative 40, which is going to become positive, and the answer that we are going to get is 100 km per hour. So that's the relative velocity, A relative to what? To B. So interpretation that is there is car A appears to move away from car B at 100 km per hour. They are separating or approaching each other at 100 km per hour. So relative velocity is all about, just from the way they're relating, it's all about relating the velocities of what? Of two moving objects or stationary objects. So that's just relative, or moving, since it's velocity, or maybe a constant speed. So example 3 that we have is train and bow. A train moves at 15 meter per second relative to Earth. This one is moving at 15 meter per second. A passenger throws a bow backward at 15 meter per second relative to the train. What is the velocity of the bow relative to what? To Earth. So what's there is when they say a train moves at 15 meters relative to Earth, which means TE, which is train relative to Earth, it's 15 meters per second. And a passenger throws the bow backward at 15 meters per second relative to the train, which means bow relating to train is equal to negative 15 meters per second. And we are asked to find the bow relative to Earth, which means when you go to the equation, you already have bow relative to Earth. So how do we find bow relative to Earth? We are going to say bow relative to Earth is equal to bow relative to train plus train relative to what? To Earth. But when we look at this equation, it was like this before it became like this. It was like this. So this equation was like this. Velocity of bow relative to train was, so it was like velocity of bow to train is equal to velocity of bow to Earth minus velocity train to Earth. Now, since we are looking for the velocity of bow to train, we are looking for the velocity of bow to Earth. We are going to make velocity of B to Earth the subject to the formula, which means it's going to be when this V TE jumps to the opposite side, it will be positive. So this is how that equation came about, whereby velocity B relating to Earth is equal to VBT plus VTE. That's how the equation came about. So we are going to find that now velocity of bow to train is going in the opposite direction of the train, so we are going to put in a negative. What about the velocity of train to Earth? Velocity of train to Earth is 15, so when you add negative 15 plus 15, we are going to have 0. So at the end of the day, to an observer on Earth, the bow appears to drop straight downward. Because the velocity is what? The velocity is what? Is 0. So what do we do in direction conversion? Choose a positive direction, usually east, and assign signs accordingly. So west is going to be negative and east is going to be what? East is going to be positive. Alright, so we proceed again. So what about relative velocity in 2 dimensions? So those examples that we are doing, it was 1 dimension. The object is just moving in one direction. What about in 2 dimensions? In one of my previous videos, I was talking about a projectile motion where an object is moving in 2 dimensions. So how do we deal with relative velocity in 2 dimensions? So when motion occurs in more than 1 direction, we solve vector equation using what? Using components. So what we mean when we say in two dimensions, imagine an object is trying to move, but when it's moving, instead of just moving straight, for example, we have a boat here. Instead of just moving straight like this, it's being pushed again to move like this. Now, when you look at this, it's in two dimensions. We have the x component and the y component straight, but now the object is something moving like this, which means it has the x component from here to here and the y component. So that is what we call what in two dimensions. Now, what do we do when in terms of relative velocity? So in two dimension, how to solve 2D relative velocity problems? So label the three objects, which is A object, B observer, and F. So you have to label those objects. Then second, for example, here are the components that are usually there. For example, Vy and Vx. Okay. 2. Identify the given velocities and the unknown. Draw a diagram and choose x usually east and y usually north. So after labeling, you have to identify the given velocities and the unknown. You have to look for the one that is not there, that is not given. For example, velocity of what? Maybe AB is not given. So write the vector equation. What's the vector equation? The same formula, VAB is equal to VAE minus VBE, but in this one, we are going to show that it's a vector, which means we are considering what direction. The fourth step is resolve all known velocities into x and y components and substitute into the component equation. So what are you going to do? You are going to resolve the velocities into x and y components. So what's going to be there is, that's where we come here. You resolve, if you have a 200 meter per second, you resolve it into components. For example, you have let's try to do an example here. So what we say when we say resolving into components, yeah, so we just resolve into components using the angle here. Yeah, so after that, you just find the speed, which is v is equal to vx squared plus vy squared in the square root, and you can find the direction by theta is equal to tan inverse the y component over the x component. So the whole essence is to just resolve into x and y components, so we can understand through an example. So here's an example. A boat can travel 10 kilometers relative to the earth, which means relative to the earth, which is boat to earth, which is boat to water. Yeah, so we pay attention to. So for this example, also the river flows east at 5 kilometers per hour. In what direction should the boat head so that it arrives at a point directly across the river? What will be its speed relative to earth? So we are finding two things here: the direction and also the what the speed relative to earth. So let's go ahead and solve the solution. So boat to water, boat relative to water, that's VBW. Here the boat relative to this water, we have VBW, which is 10 kilometers per hour. Also we have water relative to what? To earth. We have water relative to earth. So water relative to earth here is 5 kilometers per hour. Then we also have a boat relative to what? Boat relative to earth. That's a resultant. Yeah, that's a resultant now for these two. From vectors, we know what the resultant means. Yeah, so here is what we are going to do. X components, we have 0 is equal to VBWX plus VBWX. So what WEX? So VBWX, we just say 10 kilometers per hour sine angle for us to resolve it into x component, where VWEX is already 5 kilometers per hour. Yeah, so since we know that the resultant, when you add these two, it's supposed to add to 0. That's why we have put 0. So we are going to find that the only thing that we don't have is the theta. So we just resolve our sine theta. We make it the sum of the formula. So we are going to have sine theta is equal to 5 over 10, getting 0.5. So the theta that we are going to find is what? 30 degrees west of what? West of north. What about the y components? The y component is going to help us to find the what? Speed relative to earth. So So we are going to say VBEW both relative to earth is equal to VBW, which is both relative to water plus water relative to earth. When we add these two, we are going to find the both relative to what, to earth. So we're going to say BW is just 10 cos the angle there to find the y component, plus V water to earth is 0 when we see it has no y component. So when we add these two, we're going to find 8.66 kilometer per hour. That's the north. So that's our answer for what will be speed relative to earth. So that's how we solve in 2 dimensions, relative velocity in 2 dimensions. So all you have to do is resolving into what, into x and the y components, and use the formula of theta is equal to the y component over the x component. So thank you guys for watching, and don't forget to subscribe for more lesson videos.